Hey class, Adam Ward here. I want to talk to you about temporal moments. So one of the cornerstones of our short-term storage analysis, or analysis of the mass that we got back. So in order to study temporal moments, first let's talk about what the heck is a temporal moment. So I mean a moment here not in the sense of a temporal concept, like having a moment or sharing a moment with someone, but in the physics sense. And so physicists would think of a moment as a force multiplied by a distance. And you might be more familiar with that in terms of a torque, where a bolt might need to be tightened to a certain amount of foot-pounds or Newton meters, depending on what system you're working in. So for those who haven't seen this before, let's think about a wrench trying to turn a nut, right? And if we press on that wrench with a force of 10 newtons to try to rotate this at a distance of 10 centimeters or 0.1 meters away from the nut, we're creating a moment of 1 newton meter. 10 newtons times 0.1 meters gives us 1 newton meter. So our moment, or our torque, if you prefer to think of it that way, is the force multiplied by the distance. Now similarly, if I instead applied that 10 newtons but at 0.2 meters away from the nut, I would double the moment. So it would be easier for me to turn that nut because my 10 newtons of force is now applied at twice the distance away, 0.2 meters, giving me a total of 2 newton meters of force. Now, if you've ever worked on machinery where nuts and bolts are stuck, you might have grabbed a longer and longer ratchet arm or even stuck a piece of pipe over the end of a wrench to get a really long moment arm. The extension of that moment arm means that your force applied farther away gives you more torque. The other neat thing about moments is not simply that you can calculate them individually, but they're additive. So let's say that my son and I are trying to do this together, and he pulls with 10 newtons of force where the purple is shown, and I pull with 10 newtons of force where the green is shown. Our combined effect would be his moment plus my moment, and we'd actually be applying 3 newton meters of force. And so what I want you to realize here is that moments are combinable, moments can be calculated, and in order for a moment to be meaningful, we have to calculate it around some point. And by around a point, what I mean is this moment is being calculated as the impact around that nut. That's where we set as, if you want to think of it as our 0 point, and all of the moment arms were measured as a distance away from there. So it's important that we have not just a magnitude of force, but that we have a distance where that force is applied. So this is all about wrenches and nuts and torques. What does this have to do with solute tracers? Well, we use the same approach to deal with our breakthrough curves. Now, instead of having a force like the newtons on the previous slide, we have a magnitude of concentration. And instead of having a moment arm as a physical distance, we're using a time scale to describe that. And just to be really clear here, this is the normalized concentration. So I'm going to write normalized. In other words, the area under the curve is equal to 1. So we've gone ahead and normalized this concentration to have an area of 1 under the curve. So for that little strip of our breakthrough curve, we could calculate something like a moment. Instead of a force, we have a concentration. Instead of a distance, we have the time at which this occurred. So if we want to calculate moments around t equals 0, in other words, we're taking the origin as the point where we calculate moments around, from that little strip that I've drawn, the moment would be calculated as the concentration, c sub t, multiplied by the time scale, t. And if we wanted to do that for all of the breakthrough curve, we would simply integrate this. So we would add those up under the breakthrough curve. And what this would be called is a first order temporal moment. First order implies there must be something else going on. So there are higher order moments that can be calculated, and the way they get calculated is that the distance in those cases would get raised to the nth power. So in the case of a second order temporal moment, you would integrate the concentration multiplied by time squared. For a 2 millionth order temporal moment, you would do the concentration multiplied by time to the 2 millionth power. We won't go quite that high, we'll stick with first, second, and thirds in our analyses. So this is how we can calculate a temporal moment. Now, there's one other type of moment that I want us to think about, and these are what are called central moments, or central temporal moments. And so, well, on what I've shown in green, we were calculating using the origin as the basis. For central temporal moments, instead of calculating them about the origin, we're going to calculate them around the first temporal moment, or around the centroid. So that M1 represents the point at which 50% of the mass is on the left and 50% of the mass is on the right. That's the point at which that breakthrough curve would balance in the lateral direction. And so what we're going to do now is not ask, okay, what's the moment relative to the origin? We're going to ask, how is the shape distributed around its centroid? You could think of this like a normal distribution, where you think about a mean being where the maximum of that normal distribution would occur, and then a variance to describe the spread around the mean. And that's exactly what we're going to do here. We've got our first temporal moment to tell us where the centroid is, and then we're going to use these central temporal moments to tell us how the mass is distributed around that centroid. So classically, a mu is used for this, and what I've written in blue here looks an awful lot like what I wrote on the left-hand side. The only difference being, instead of time, we've replaced it with t minus m1. So the distance from that central temporal moment. Right? So we're measuring relative to that blue dot that's drawn on the screen right now. And again, you don't just have to do that as a first order. You can do that in any order you want. So an nth order central temporal moment, mu sub n, looks like the equation written in the bottom right. And you'll see all I've done is take that t minus m1, that moment arm, and I've raised it to the nth power. So who cares about all of this? Well, this tells us some really important things about transport. And so, as I've already said, the first temporal moment tells us about the median arrival time. So it gives us the time scale at which half of the mass has already passed and the other half has yet to arrive. It will not necessarily be the highest concentration, but it will be the time at which 50% of the mass has passed. So that's a time scale that's related to advection. The second quantity I want you to be familiar with is called the coefficient of variation. And so just like we talked about a normal distribution having a mean and a variance, or a mean and a standard deviation, that's sort of what the coefficient of variation does here. It gives us the spread around the mean. So we can calculate this as the second central moment, mu2, raised to the 1/2 power, or the square root of mu2, divided by mu1. And the reason I find this one really informative is it gives you spreading relative to advective time. So if you're working in two systems, one that's very fast, one that's slow, maybe you're working in the same system under low and high flow conditions, we need to separate the spreading from how long that process has to happen. So coefficient of variation gets us spreading per unit of advective time scale. That's a really nice transferable metric that we can use to compare between really different systems or really different flow conditions. So spreading normalized by advective time scale is what I want you to know about coefficient of variation. The last one that we'll talk about as a group is going to be skewness. And skewness is the third central moment, mu3, divided by the second central moment, mu2, raised to the 3/2 power. And what that skewness is telling us is how symmetrical or asymmetrical is the distribution. So a normal distribution is perfectly symmetrical and would have a skewness of 0. If your study looks like the green breakthrough curve that I've sketched here, the skewness should be greater than 0. In other words, the tail of your distribution points in which sign the skewness should be. So if the tail is pointing in the positive direction on the x-axis, it's positively skewed. If you get back something that looks like the purple, you have negative skewness. Now, in our solute tracer studies, we are always expecting either no skewness or positive skewness to be the case. And our interpretation here is that the more skewed the distribution, the more transient storage impacted the transport through the study reach. Okay, so at the end of this temporal moment video, you ought to have some conceptual understanding of what moments are. You should be able to calculate temporal moments and central temporal moments. You should be able to use those to calculate median arrival time, coefficient of variation, and skewness, and have some interpretation as to what those metrics mean. All right, time for you to practice in your next learning activity, and I will see you back here for our next topic. Thanks all.